does that do?
What
That-
one? April?
The integral one.
The one that's just 3 questions?
Yeah.
Tomorrow.
Is it tomorrow?
Yeah.
It's cool. Let's see how that goes. Let's see if we can get it done by tomorrow. If we need more time, we can talk, get that hooked up. But no direct questions on that right now. Let's start with some warm up. All right, cool. So just real quick while I'm getting this up here, think to yourself, what are the series? What kinds of series do you know? So yeah, we're just gonna do a little warm up, karma-free quiz. Okay, yeah.
Geometric.
Geometric, awesome. And
P-series.
P-series, awesome. And
Harmonic.
which is a kind of P-series, but yeah, it's a good one to know. Absolutely, it's a good one to know, yes.
Telescoping.
And telescoping, solid. Awesome, let's put that up here. That's all good shit. And knowing the harmonic is good. That's like a very special place. So, types of series. And then we have some conditions with those too. So type of game, am I recording there?
Yeah, you're
All right, thank you. Types of series. So first off, let's go there. Geometric. So a geometric series has some constant times some common ratio, getting higher and higher powers, and this can start lots of places. We'll just start at 0. It doesn't matter where we start it. We can always work this through. And this converges to, in fact, it converges to the first term over 1 minus the common ratio if what? What do I need for a geometric series to converge?
R is less than 1.
Absolutely, the magnitude of r is less than 1, solid. All right, so we got that. We own geometric series completely. And then the next one, Scotty mentioned for us, P-series. So P-series is a series that's kind of the flip of a geometric. Here, notice up here the exponent is the moving piece. Down here the base is the moving piece. We have a fixed exponent. That's the hallmark. That exponent, usually we start at 1, go to infinity. This series, we don't have a nice formula for the sum of. In fact, these are really complicated. But this converges if what? When do these converge?
P is greater than 1?
If P is greater than 1, solid. So let's actually talk, and Abraham had mentioned the harmonic series. Let's put that in here because that's the dividing line here. So we have the harmonic series, which looks like this. It's 1 plus a half plus a third plus a fourth. And that diverges, right? Because P is equal to 1 here. So this is P equals 1. That's the harmonic series. And this diverges. If P is greater than 1, then we converge. So here we've got series that look like this. 1 over 1 to the P plus 1 over 2 to the P, 1 over 3 to the P, on up. That will converge. So above that, and then below it, if P is less than 1, then we have, well, actually, here, let me make a specific P, like 2 squared, 3 squared. That's going to converge. If I'm down here and I have fractional powers, so for example, square root of 2, 1 over the square root of 3, this is going to diverge. So we understand harmonic, yes ma'am?
So in the geometric case, it can include the absolute value of R for determining convergence, but is it not the absolute value of P in a P series?
Correct, yes, absolutely. Yes, good observation there. So we got P series, and then we also talked about then telescoping. So first off, just make a note here. Can't find the sum of these without math beyond calculus. unlike those up there. And then we have these telescoping series. That word is telescoping. That looks really freaking weird. It's very distorted. But a telescoping series, I don't really know how to put those up. I'll put an example up. We've got something like 1 over n plus 2 minus 1 over n plus 3, n equals, I don't know, 2 to infinity. But what we had here was that the partial sums collapse. And we can get a sum. It's just a special, those are very special and weird and occur pretty much like only in Calc 2 classes in a way. Sometimes you luck out and you can find them elsewhere. So, but this is what we know. Let's take some tests now here. Converge or diverge. And every day we come in, we're gonna do some practice with this, and we're gonna kind of review everything so you see this over and over again. So I'm gonna give you a couple series. I just want you to take a minute. Let me know, does this series converge or diverge? Oh, and there's one other thing we hadn't talked about. Hold on, let's get it up here. What is the divergence test? We had one more thing, and it wasn't a type of series, but we had this test called the divergence test. What was that test? Yes.
If a to the n does not converge to 0, then it diverges.
Absolutely. Then, so if I have a sequence of terms and they are not dying out, then this series diverges. Here's a quick true or false test. If the series terms die out, then the sum converges. Is that true or false? It's kind of like the flip of that one.
No. We don't know. We don't. It just doesn't mean anything.
Absolutely, we don't know anything, right? This is false. This one here, we don't know. Just like Abraham said, that was very nice. So we don't know. I mean, because look up here, look at the P series, right? In the P series, your terms look like this. They all go to 0 as n gets bigger. So down here, everything's shrinking to 0. Sometimes it's not shrinking fast enough so that we can get a finite sum. So don't make this mistake. That is not a test for convergence. It's only a test for divergence. So could you just take a minute, my friends, and go through these and just quiz yourself. Can you determine if those are converge or diverge? This is like, it'll be something like this on our final. Let's talk. Why not talk? Yes. Yeah. So what is converging here, though? Is it the series or the terms of the series? just like, one of the things, and I'll talk about this, but one thing, when you say this, like, then give a quick little reason, you know, you say like, here, diverge, P series, P equals a half, something like that, needs to have a little bit of, little justification.
Are we determining the point of convergence or just whether?
Just if, yes, just thumbs up or thumbs down. If you get bored, you know, there is that, there is one that can be summed up. Oh, you're thinking, yeah. Yeah. There you go, yeah. Okay, cool, good. Yes, so yes, because this is actually 1/5 to the end. So the whole thing is the R here. 1/5 is your R. Oh, does that make sense?
Okay.
Yeah. I kind of wrote it like that to be a little tricky, so. Good. How about we come together and talk here at Friends? Let's check in, see what we're thinking. So this first one, the 3 doesn't, these numbers that are in here don't mean anything, right? They can just come out in front. So no constant can ever affect divergence or convergence. This one here is a P series with P equals a half. You see that? That's n to the 1/2. So one of the things, and I was telling Voight this, that when you say diverge or converge, get used to providing a little bit of a reason. So I'm going to say that this diverges because it's a P series with P equals a half. Does that make sense to everybody? Does that sound okay? Good? Okay, awesome. This one over here, a P series as well. So this one does converge though, because here the exponent on the end is 3 and that's bigger than 1. So this converges because it's P series with P equals, I guess that's a 3. If you said 2, that's okay too. It looks like a 2 as well. But I think I meant a 3 there. And then down here, this one's a little bit tricky, but here's the key. See that n is the exponent. The thing that's moving is the exponent, so you immediately start thinking geometric. And this one's a little bit of a trick because you have to see that it's actually this series right here. What is being raised to the nth power? It's not 5, it's actually a 5th for each term, because what are your terms are going to be 1/25th, 1/125th, 1 whatever the hell the next one is, next power of 5. So this converges because it's geometric with r equals 1/5. So I'm just giving a little bit of a reasons. And then finally this one, you go through and you think to yourself, is it a P series? No, because there's an n on top. There's an n on the bottom, but there's also this like n plus 3 on the bottom, and I don't have it up anymore, but that's not what our P series look like. So it's not a p-series, it's not geometric because there's no exponent moving. So no moving exponent. That means it can't be geometric or even related to a geometric. And so I mean, I could like think about that integral test that we're gonna talk about in a minute, and we talked about a little bit last time. Or I could hope that this might diverge. And I noticed that this thing here, you've got an n on the top and an n on the bottom, and if you think about it, these things are headed to 2 as n gets bigger. And that means that the terms are dying out. Think about what this means. That when you're way out, right? Like what's your first term? 2 times 1 over 1 plus 3, and then your next one's 2 times 2 over 2 plus 3. But eventually, way out, essentially what you're gonna have is 2 plus 2 plus 2 plus 2 forever. That just keeps building up. That's what this divergence test is all about. Eventually out there, I'm not 0, so I just keep piling up. So this one diverges by the divergence test, sometimes called the nth term test. So diverges because a sub n goes to 2, which is not 0, so by the divergence test. Any questions on any of that stuff, friends? Yes, Dan?
On the last one, couldn't you also just take the limit of 2n over n plus 3 as n goes to infinity?
Yes, and I guess that's essentially what I'm doing right here when I say this. What are you thinking of something? Explain maybe a little more what you're.
Well, you take the limit as n goes to infinity, and then you L'Hopital it because it turns into infinity over infinity, and then turns into 2.
Absolutely, yeah. So absolutely, and as long as, and that's essentially what I was kind of arguing here, but you're right, and yours is a little more detailed, so just say divergence test and provide that argument, you're good. Yes?
Why do we have to look at the third one as 1 over 5, not just to the power of n, and not just 1 over 5 to the power of n?
Well, because we're trying to look for, well, if we're viewing this as a geometric series, how would you, I mean, you want to have this whole term be something to the end, so what is being raised to the end to get that? Does that help?
Yeah.
I wasn't quite, I was like, that's a good question, I'm not quite sure. So, if you buy that, then I'm happy. Any other questions on this? All right. So let's do one more. What if I had this one here? I'm going to walk us through this one. That's a pretty weird one. Let's write out what it looks like, just so we have a sense of it. That is, notice how I started 2, because the natural log of 1 is 0. And I don't want to start things off by dividing by 0. That's a bad day. So we got 1 over 2 natural log of 2. 1 over 3 natural log of 3. 1 over 4 natural log of 4. On down the way. That is a pretty weird series. One thing I know is it's not geometric because there's no exponent. It's not a p-series because this screws that up. So it's not geometric. It's not a p-series. Let's check out the nth term test. So a sub n is 1 over n natural log of n. When I take that limit as n goes to infinity, what is that limit? Somebody help me out here?
0.
Exactly. Yeah, nice. Yeah, top's fixed at 1, bottom's blowing up. In some complicated, weird way, but blowing up nonetheless. So yeah, absolutely, Scotty, that goes to 0. Nice. Sophie, was that a question, or just like your hand was just like looking like a question?
Maybe there will be a question for
Okay.
okay.
All right, cool. So this doesn't tell me anything. So the divergence test doesn't apply. Doesn't help. Right? Because it doesn't work that if they go to 0, that gives you convergence. So for this one, I'm kind of at a loss. But I do have this that I wrote up on the board, and I'm gonna show you. This is actually the way to do this one. If you see something that has a sum and it's not something easily accessible, but if you replace the n with an x and you can integrate it, then that's a good approach. So let's try the integral test. So the integral test would say I'm going to integrate and turn the sum into an integral sign. I replace the n's with x's. If this turns out to be finite, then the sum converges. If this turns out to be infinite, then this diverges. So it's kind of a cool thing. We just got to figure out how to do that integral. Let me help you remember how to do this. We're going to use u substitution. So we're going to let u be the natural log. Then du is 1 over x dx. Look how pretty that was. Look how lovely that turns into. So this part right here, that's my du. This is my u right here. So this is going to be equal to integral of 1 over u du. Now we got to adjust the limits. When x is 2, u is natural log of 2. And natural log of infinity is infinity. So now I've got a decent integral. It turns out that, oh geez, it's another natural log. So this is natural log absolute value of u from, I'm going to cheat here, a horrible abuse of notation. That means take the limit there, but I just kind of wanted to get to it. This is infinity. The key thing is this part here is going to blow up as the u approaches infinity. So this integral diverges. It equals infinity. So that means this sum also diverges. This would not add up to anything finite. So this diverges by the integral test. Always at your disposal if all else fails. Does that sound all right? Yeah, not bad. Yes, Sophie.
What happened to the previous integral of 2 to infinity? Why did it become natural log of 2 to infinity?
Oh, this is a natural log form here. So, right, so because I've got just this.
Oh, that was just one of the...
Yeah, one of the steps along the way. Yeah.
Okay.
This was after substitution, it turned into this form, which is a natural log form.
Okay.
So that's where the natural log of u came from. And then I just kind of shittily used infinity as a number.
Okay. Cool.
That's not okay. I'm telling the camera and who's ever watching. Yes?
Why do we need to make that adjustment?
Which adjustment?
Adjusting the limits.
Oh, well, because this original integral was in terms of x, so the x ran from 2 to infinity. But now I'm changing what the variable is, so I need to have the range of the u reflect the range of this u, because the original reflected the range of this variable, so we've just moved to a new variable. I gotta make sure that we've got the limits to be the same, or consistent, is what I mean.
Okay. That's,
Yeah. Other questions? There's a lot of good questions. Cool. Let's check out another one. We also talked about some comparison tests. So keep in mind what we've got here. You've got 2 series you understand. So your only series we understand, and this isn't going to change, understand, are geometric and p-series. These are our references. This is our map. We base all our understanding and all future conclusions on knowing completely these series. And we're going to always try to relate back to them when we can. It's not always possible, but sometimes it is. And the way we get to these is we're going to use comparison tests. So comparing a given series to one of our known series, is pretty much the bulk of our work. And it's just how to compare them. So last time we talked about the direct comparison test. The DCT comparison test. So let's see how did that work. That said that if our series are positive, we don't have any negatives in the series. There was one question on the last web work, I guess 12, where this wasn't met. I think Gabe, you had asked me about that one. There was one of the statements was false, but it was because the series didn't have positive terms in it. So if this is the case, then if this thing converges and this series, this B series is bounded above by this one, in other words, the sum I'm about to write is underneath this one, then it converges. So remember, this is just shorthand for converges. When I write less than infinity, that means it adds up and it's finite. So check out how this works. I've got something that I understand, I've got something that lives underneath it, then this thing that lives underneath it must also add up to something finite. And we have this version here that if, let's do it this way, if B sub n diverges and B sub n is less than or equal to A sub n, then B sub n itself, then A sub n diverges. This one's underneath this one. This one lifts this one up to infinity. If this goes to infinity and this one is above it, it's pushing it up as well. And I want to make a little comment about this part right here. This just means eventually. It doesn't even have to be for the first 1,000 terms, but eventually and then forever. Forever after. So this might not be happening the first 5, 6 terms. As long as this happens inevitably and doesn't change, this is usable. So let me show you how to use this. All right, so example. All right, let's look at that one. Looks like a P series, right? Kind of. Okay, point's more skeptical. I like that skeptical. He's not going to accept this then. What kind of P series does it look like? P equals 2. You see that? It's kind of like the P equals 2 series, but it's not. How does it compare to the P equals 2 series? So this is kind of like.
Can you have like a telescoping P series? Is that a thing?
Ooh, I wish that would be possible. This one, we can't factor this, unfortunately. If we could, that would be a neat way to maybe approach this, but
Okay.
yes.
Since there's a +3 in the denominator, doesn't that mean it's technically lower than 1 over its square?
100%. Yeah, exactly. So check it out. You're adding more to the denominator that makes the term smaller. So since this thing here is always, it's not even ever equal to it, it's always less than that for every n. If this converges, then this converges. Then by, and let's see, let's write this out. Since this is true, and this converges, then by the DCT, direct comparison theorem, our series converges. So you can kind of argue that way. It's not a bad, make sure that that's making sense to you, and if not, ask me about it, and let's talk about it. How about this one? So ask yourself, what series does it seem like? What does that series do? And then what does this one do, and how do I argue that? So we're going to practice just building up these arguments today. I'm not going to give you any more web work until Wednesday, so just focus on this. What do we think it's like? So,
It's like 1 over n to the 1/2.
yeah, it's like this, right? It's that square root of n. Does this converge or diverge?
Diverge.
This diverges. So if this one is bigger than this, then I'm good to go. So I suspect divergence. See, I see this. See, it's like this, so I suspect divergence. And so now I'm all about showing the divergence. Nth term test isn't going to work, or the divergence test isn't going to work on this. So there's only one way to do this. So notice that 1 over the square root of n minus 3 versus 1 over the square root of n. Which one of these is bigger? The left or the right?
Right.
The right, yeah, because here you're making the denominator smaller, right? So this is the case. Oh wait, this is the case. Sorry, smaller denominator means bigger fraction. Yeah. So this one's bigger. Notice I started at n equals 5. There's no worries about dividing by 0 or anything like that. So let's see this. This and this diverges.
Wouldn't we have to divide by 0 at n is 9?
As we would. Oh shit. That's it. Oh shit. I was trying to skip it. Yeah, thanks, Abraham. Now let's boot this up a little bit. Let's start up there. Thanks. Yeah, good one. I was trying to avoid it. I don't know what I was thinking.
'Cause I was also thinking, like, if it was 5, then wouldn't that first one be a negative number, which would be less than the other one? Or
Yeah, it would. There would be a lot of really big problems. So thanks for catching that. Yeah, let's start at 10 so that doesn't happen. So this is true. This diverges. So this series must add up to more than our given series by the DCT. And that's all you need. You don't have to write an opus, just a couple lines of reasoning are going to help with that. Any questions on that, my friends? Oh, yeah, Gabe.
So what would happen if it was less than, though, on both cases, like if it was the opposite sign?
Oh, like it was like this?
Yeah.
That's great. Well, I love that question. Let's do that. So Gabe is asking, let's just come over here and tweak this one since I already got it. What if it was like that? Right? So let's just take a look at that. Yep, this is kind of like that, but let's see. So let's actually do this in an interesting way. That is definitely less than that, right? So if you take the reciprocal of both sides, you have to flip the inequality, right? When you have an inequality and you take reciprocals, you have to flip the inequality as well. So I got that, but this converges, and so this one's above it, so I don't get that crushing effect. Because this series lives above this series, I can't use this argument to show convergence. So no comparison is possible. No useful comparison is possible. It's just going in the wrong direction. Is that kind of what you were asking?
Yeah, that
Okay,
was-
awesome.
thank you.
Cool. Yeah, great question. Really great question. But what could we do here? It sure seems this is so freaking much like this one. It seems like this has got to converge. How could we show that? This is the test you're going to want to use most of the time. The problem with some of these tests is you have to like get into some deep thinking, and maybe you won't see the relationship. Maybe it's not obvious. So that's where we have this useful test called the limit comparison test. This one's great. Comparison test. So let's talk about this one. Again, I need a comparator, and I'm only going to grab from my bin of comparisons over there. But the limit comparison test says this. Given two series, A sub n and some B sub n, and let's assume that all the terms are positive. If the limit as n goes to infinity of the ratio of the terms. So now look there, I'm pulling away the sum, I'm just like looking, what's A sub n, what's the formula for that, what's the formula for B sub n, and I put them in a ratio to each other. I'm gonna rewrite this in a way that you're probably gonna wanna also do that. That's A sub n times 1 over B sub n. Sometimes that's a useful way to think of that. If this is equal to some number gamma, and that number gamma is not 0. So check this out. I'm saying that this limit exists. It's equal to a positive number, i.e. equals a positive number. If it's equal to 0, we don't have useful information in general. But if this happens, then those two series act the same. They act the same in terms of convergence or divergence. Then some A sub n and some B sub n either both diverge or both converge. So this is going to save our butts right over there. So let's come back over here. Direct comparison was not working here. So I'm going to try a limit comparison because damn, that thing is so much like p equals 2. It's crazy. So let's apply the LCT. And it doesn't matter, just a little note, it doesn't matter who's A sub n and who's B sub n. Does not matter at all. Yes,
Do
sir.
we have to change n to be 1 in this case so we don't have any negative numbers in there?
Actually, we should change n to be something much bigger than 9, just like on that last, or 3, right? So how about there? There we go. Thanks. You're keeping an eye on my series for me. I appreciate it. You're like tender of the series, the shepherd, series shepherd.
Doesn't it just have to be greater than the square root of 3?
Yeah, I guess so. So
Yeah, it would just have to be 2.
two or more. Yeah. I was just trying to cram it up real high there, but yeah, agreed. I like it. I like the concern over the details. Very lovely. So here, this could be A sub n, and this could be B sub n, or vice versa. But in essence, what I want to do is I'm going to take the limit of, and I'm going to write this both ways. Let's put this one on top, and put this one on the bottom. You're not going to want to do that. You're going to want to rewrite it like I suggested. So that's n, limit as n goes to infinity of this one, n squared minus 3, times the reciprocal of this one. Look at how much better that is. And that's what you have to do to simplify this anyway. So now I've got lim as n goes to infinity of n squared over n squared minus 3. What's that limit? 1. Yeah. Do we see that? 1? Yeah. When n is really big, it's essentially n squared over n squared, right? When n is a billion squared minus 3 is still pretty much a billion squared. So this is 1. You could L'Hopital it, you could do whatever you need to do to see that, but that limit is 1. That's not 0. So by the LCT, this acts like this. So this series converges like this series does. That's a very useful, very powerful test. And so let's try some stuff now. That's it. That's the only test I'm showing you today. Pretty much every day we're going to come in and we're going to see like a new test. So my friends, can you please do these series here? We have got, here's a fun little, okay, so this one here, let's just do this together. I've got that series. A and B are positive numbers. Does that converge or diverge? Take a moment and create the argument. And you use the LCT. You'll have to use the LCT. Yeah, exactly. Yeah. That's your intuition. Absolutely, that's correct intuition. And then use the LCT to prove that. Yeah. We just went through the process that you want to be going through. What do you think it's doing? What does it look like that you know? Get that intuition, then demonstrate that you have it right with one of the tests. It's an interesting face. Yeah. Question. That looks good. Yeah. It's looking good. Yeah. No, so don't use a sub and put it in. What are you comparing to?
The A sub n or A times?
Well, I'm not sure what that. Oh, okay. So what series are you comparing to? So what is, and it should either be just a P series or a geometric. So yeah, I think you're comparing to something else. See what I'm saying? Yeah, yeah. So friends, you want to be comparing to the harmonic series here, right? This is like a P series with P equals 1. So compare with the harmonic series. And so if you're doing that, you're suspecting divergence. You wouldn't do that otherwise. I'm just putting here, you can do the comparison, doesn't matter who's first, who's second, all good, can't go wrong. Get a different limit out, but that doesn't matter. What do we get on this limit? 1 over A, yeah, we got that, cool. And why is that not 0? Because A is positive, right? So that's a nice little positive number. If A is positive, so is 1 over A, Gabe.
Oh, wait, so that wasn't A sub n, that's just A n?
That is, yes, that is
A
A
times
times
N.
N.
Okay,
Yeah,
sorry.
yeah, yeah. Oh, I can see, oh, that's, yeah, I can see where the confusion came in, yes.
Where did the B go? Or are we just assuming that the A kind of?
Well, the B, when you do this limit, Sophie, the B goes away.
Oh,
so-
right, because that would just be.
Think L'Hopital's rule,
Oh, okay.
right? You got
Sure.
derivative tops 1, derivative bottoms A.
Okay,
Yeah, yeah, cool. Good. And then, did anybody actually do it like this? Just out of curiosity? No. It's cool. If you had, you did? Yeah, nice. So you ended up with an A, which is still positive, and perfect. Can't go wrong.
So that means it converges if it's positive.
That means these act the same. The fact that this limit turned out to be positive means this acts like this.
And if that converges.
But
then
what does this do? Harmonic series.
That would diverge.
That diverges.
Right.
So that diverges.
Okay.
Does that make sense?
Yeah.
Yeah. So you can get converge or diverge out of this test, Sophie. It just depends on what you compare to. If you compare to a divergent series, then you're going to conclude divergence. So this diverges by the LCT. Okay.
So just as long as it's greater than 0, then it's gonna follow suit with the, okay.
Perfect, nicely said. Absolutely. Let's try an interesting one here. What about this series? We've got n squared minus 10 over 4n to the 5th plus n cubed. I'm not gonna put indices on here because it doesn't matter. It won't matter. I mean, it really doesn't matter. Assume there's infinity on top. That's all we care about. We don't give a shit about the beginning. We only care about the end of how these things go. So look at this together. Let's just take a moment and then let's rejoin. What do you think you're going to compare to? Because this is trickier now. Now we're going to start having to come up with some things. What will you compare to? You seem like a telescope. Oh, no. And in fact, let's just make a rule. We'll never compare to telescoping series. Let's close that off-ramp down. We're only going to compare to geometric or P series. If you got a telescope, then you just deal with that sucker on its own. Yeah. ask yourself, what is the dominant thing on top? What is the dominant thing on the bottom? What is this like when n is really big? That's the question you're asking yourself. What is this like when n is big? So right now we're just seeking a comparator. Anybody got any help for me on this one? What do we think this might be like when n is big? Abraham?
Geometric.
What's that?
I'm not sure I have a word for it. Kinda looks like a P series with P greater than 1.
Definitely got some P stuff. Definitely not geometric, right? Because there's no moving exponent. So we know that. So we're thinking P series. Notice that when n is really big, the minus 10 doesn't matter, right? So when n is like a billion, it's essentially n squared. On the bottom, this n to the fifth completely, when n is big, this completely overrides this. When n is 10 to the 10th, this thing here, n to the fifth, is 10 to the 50th. N cubed is 10 to the 30th. This is the part that's dominant. When this is this is this. The major action is happening on this big exponent here. So this is essentially this when n is big. The n cubed doesn't matter relative to the n to the fifth when n is big. That's the key here. That's the disclaimer. When n is big. And what is that approximately? That's like n squared over 4. That's like 1 over 4n cubed. That tells me I'm going to compare to the P series P equals 3. So let's try that. Compare to, so note it's just the net effect of the major exponents, just a ratio of 3. Compare to this series. So I'm suspecting convergence because I got P is bigger than 1, so I think this thing converges.
Can you explain one more time why n squared is just 1?
So I'm canceling. So I'm saying when n is really big, this, did you buy this part here?
Yes.
Okay, cool. So then notice that you can actually cancel. I just
Oh.
canceled out that power of 2 from the top and bottom.
Gotcha.
Yeah.
And you don't need the 4 because at that point, if it's big, it's just big anyways.
Yeah, exactly. Yeah, and then when we go to get our comparison series, this 4 would just create a different multiple of things. So, yeah. So we're just going to compare to this guy here. Yeah, ignore the constants, all that. Go for the heart. What is that limit going to be? Yeah, that's right. Got enough fingers on one hand to do it. 4? Yeah. You want to be able to do a limit like this in your head. And here's how. Notice that these are just polynomials in n, and they have the same degree. 5th degree, 5th degree. The limit is just the ratio of the leading coefficients. When we have n big enough, well here, let me actually prove that to you. You may or may not believe that. You could L'Hopital this thing like 5 times if that's your, your thing you enjoy doing. But this thing here, if I divide the top and bottom by n to the 5th, so I'm multiplying by 1 over n to the 5th on the top and bottom, I get that. And then this, we see, I know everybody believes that. So then the whole thing just goes to 4. So there's a couple ways to see this. Make sure you see it in some fashion. But what does that tell me? What does that 4 mean? Does that mean the sum is 4?
Means they both converge.
It means they both converge. Yeah, I'm just asking asshole questions now. Yeah, Daniel.
When you multiply the two series together, where did the
Right
4?
here.
Yeah, where did the 4 go for the n cubed?
Wait, so let's see. So I flipped that, right? So I got that here.
Which multiplied by 1 over 4 n cubed.
Oh, I see what you're doing. You could, but there's no need to keep that. So this thing here is, this 4 is irrelevant. What I'm looking for is the heart. Like, don't worry about multiples of that. Even if I had like a 30 there and a 7 on top, I would still be just looking at this part. So don't worry about constant multiples. You could keep it in. Well, let's do it really quick and I'll show you. It'll be okay. Let's see, where would it go? Here, yeah, like that, and then down here. And then I would get 1 out instead. But I would still have the same conclusion since it was not 0. But I'm saying, like, just always go to the raw P series, not a multiple of them, just to save getting stuff in there. So, yes, I'll work, yes, Cam.
So for the LCT, does it only work if it's greater than 0? Can it ever be less than 0?
If both series are always negative, no, it can't be, no. Only positive. Because we would never use this test if there was alternating signs in here that were positive and negative. We would only use this if everything was positive.
Okay.
So that's a good question, yes.
Would we have been able to pick something else to compare to? Like, are there options, or would that kind of have to be what we?
That would be the only one that's gonna give us, that's the perfect pick here.
Okay.
So there are other things, but the test will fail on them. So like I might try to compare to a different P series. Like, if I had compared to a different P series, this limit I think would have turned out to be like 0 or infinity, and it wouldn't have been super helpful. So there are options, but they're only like, am I going to include the 4 or not?
Mm-hmm.
So you really have to get the precise thing that models the heart of the action.
Okay.
And it doesn't matter what you take the reciprocal of,
Correct.
as long as it's greater than 0, then okay.
100%. So like if I had done this a different way, instead of getting, instead of getting 4, if I had flipped it, I would have gotten 1/4, which is still positive, so it's all good.
Okay.
Lots of good questions. Let's do one last one. That seems jerky. So let's just do something a little calmer. Converge. It's actually, let's make this n squared and make life a little bit better for us. There are 4 routes I think you could go here. You can use direct comparison. You can use limit comparison. I think you could do each of those in 2 different ways. this crazy thing looks like. Yeah, there's a couple people I always used to. Gabe, what was it I owed you?
Test.
Oh, the test corrections. You didn't get that test back already?
No, I wasn't here last week.
I have it with me. We know you got a grade, so.
You're talking about for exam 2, right?
Yeah, yeah.
Because I didn't make any test corrections for exam 2.
Huh. Shit, what? I thought I handed those back before last week, though. I definitely handed those, it wasn't last week that I handed those back, because corrections I handed back last week. I think you might have it, my friend.
I don't have anything about the exam 2.
Well, I'll have to take a look around.
Okay.
Yeah,
No.
You've seen your grade, though.
Yeah, I saw
Okay.
my grade, yeah.
Okay, yeah. So the grade, let's see, wait. Okay, wait, there's Isaac's. Well, I don't know, I gotta look around, Dave.
Okay, yeah, no worries.
Yeah, I'll, if you, remember to send me an email to remind me, that would be great.
I
Yeah.
also don't have money either.
Oh, okay. Wait, here's a bunch of stuff. Okay. Let's take a look. This looks good. Yes. There we go. I got one for Jeremy too, but where's Jeremy? Nobody knows.
So I never made corrections on it though. I never got it. This is the first time I'm getting it back.
Yeah.
actually.
Well, it's, that's long gone though, that time to do that. You don't need to anyway. You're doing great
Yeah.
there.
Okay, thank you.
You're welcome. Anybody, what do we think? Converge or diverge? What's it look like? Couple things, right? What are the two things it looks like? What's the one?
Geometric.
Geometric looks like, so this looks like, very vaguely like, right? Does that converge or diverge? That converges, so it looks like that. What else does it look like?
P-series.
A P-series, right? So I'm seeing, it's like a combo of these two series. That converges too, because that's P bigger than 1. So I'm seeing like this weird combo of two P-series. How could I do this with direct comparison? So how does this relate to this?
It'd be smaller, right?
Absolutely, way smaller, right? But also, I could do this. This is also true, right? Right, making the bottom bigger, right? Adding something to the bottom down here. So I could direct comparison with either of these. These both converge. Since this is true, whatever this adds up to, or this adds up to, this is less than it. So it's certainly finite. So by DCT, this converges because both those converge. Did anybody do a limit comparison? Oh, this might not work out that great.
I started it, but
Successfully.
I decided against it.
Yeah, that's not bad. This is so clean, right? Does this look good? This is like beautiful. It's like you cannot freaking go wrong with the way this is set up. I actually think the limit comparison might give us 0. Is that what you got?
Yeah.
Yeah. So you have to. So here's a little tip. If using the LCT and you have convergence known on the bottom, and you have your unknown on top, but you know that this one does converge. Yeah, the thing that's on the bottom, the key is it has to be the one on the bottom. Does converge. Then if this is equal to 0, then you get convergence. This is like one time when it's okay. Here, and only here, 0 gives convergence. And then there's this other little, the flip side of this is if I have my known on top, known diverger on top, over the unknown, the thing that I'm testing, and that goes to infinity, then the unknown goes to infinity. But it has to be in this, check this out, it has to be the converging one on the bottom, and the one I'm testing on top. Down here, if I have the divergent one on top and the unknown one on the bottom and I get infinity, then I've got divergence. That's just a weird little subtle case there. Oops, sorry. Alrighty, friends, no new homework for you till Wednesday. Say that part quietly. So, finish up the integral test. Let me know if you need more time on the integral test. See you tomorrow. Let me know. I'll see y'all on Wednesday, which is the end of our week.
I really don't do it. I'm highly debating this one.
I kinda wanna go in.
If I get what we're doing from,